Okay, let's go ahead and get started. I'm going to get the sign-in sheet passed around. Just so you're aware, we're currently working on getting homework number 1 graded. My goal is to get that back to you on Tuesday. I'll also distribute a solution to the homework on Tuesday as well. I'll put that on Blackboard. And I'll do that for all of our assignments. I'll make sure that a solution's distributed so that you have that. But yeah, my goal is to get that graded for you over the weekend. Don't forget that you have homework number 2 due on axially loaded members, and you've got everything that you need to complete that assignment except for the last problem, which is on thermal loading, which is what we're going to talk about today. You should be able to handle the majority of that, that assignment today. There's also one other sort of related topic on the homework that we're going to talk about today, and that's redundant forces, and that'll become a little clearer when we get into lecture, and I'll mention that and how it relates to your homework assignment. But we're going to spend most of the class talking about thermal loading today, and then that'll call it for axially loaded members. In other words, members being yanked on, either in tension or pushed on in compression. After that, we may try and talk a little bit about torsion. In other words, what happens when you take a member and you twist it. Axial loads and torsion share some very similar math. The equations are very, very similar, so the two topics go really well together. In axially loaded members, we're trying to determine how much a member stretches, where in torsion, we're trying to determine how much a member twists. So we're dealing with shear stresses instead of normal stresses and angle changes instead of deflections. But in the end, a lot of the equations, they're very, very similar. So, but that'll become clear when we talk about it. Any questions about anything before we get kicked into stuff? All right, okay. Let's start talking about thermal effects. I think you will find that the idea and the theory surrounding thermal effects is not that it's not that difficult, and how we handle it is pretty straightforward. But some of the examples that I've got for you today, particularly our first one, is gonna it might surprise you in terms of some of the results that you can get from thermal analysis. Now, pretty straightforward. This goes back to a principle that you probably remember from science or high school chemistry or whatnot, but if you have an object and you heat it up, it tends to expand, and when it cools down, it contracts. And so the way that we handle that from a mechanics standpoint is we use this term alpha. Now, alpha is the name for that, what we call it, it's a coefficient of thermal expansion. And basically, alpha is a material-related parameter that'll tell you how much strain that you get per degree change. So alpha will be some value, and it will be, some value like, 1 times 10 to the -5th or something. I'm just making that up. And it'll be that value per, let's say, degree Fahrenheit. So if your member has a temperature change of like 50 degrees, you would take that alpha value, multiply it by 50 degrees, and then that would tell you how much strain that you get. And I would think it makes sense that your value relates to strain because, remember, strain is related to deformation, how much a member gets longer or shorter when it's under load. If you heat something up, it expands. If you cool it down, it contracts. So it would make sense that that we're talking about strains, really, when we talk about thermal analysis. Now, alpha is another one of those material-related parameters. It's a material constant. There's a different alpha for steel than there is for aluminum, and there is for plastics and concrete and so on and so forth. And there's a list of alpha values in Appendix I in the back of your book. One interesting thing about this, and I should have mentioned this, earlier in the semester, but I'm a bridge engineer. That's my area, so I tend to do a lot of references to bridges. So I apologize to you mechanical engineers in the room, but that's just what I know. But there is something really, really interesting about alpha values as it relates to bridges. So I'm sure that even if you're a mechanical engineer, I'm sure you're aware that one of the common options that we use for civil infrastructure is reinforced concrete. We'll have concrete and we'll put rebar inside it. Well, that is outside. And, like take the parking garage here on 3rd Avenue. It's a big reinforced concrete structure. Well, I mean, here recently we've been hitting 90s, you know, in terms of temperature, and when it hits February, it's going to get kind of cold. So that building undergoes a very significant thermal loading, has a significant change in temperature. One of the things that's interesting about concrete and steel is while concrete and steel and the other's a metallic alloy, they have very similar alpha values. So when they expand and contract, they tend to expand and contract at the same rate. See, if you've ever seen rebar, you notice how it's got those little ridges, those little indentations on the end of it? Why do you think that's on rebar? Like, why do you have this? Why are there little ridges on rebar? So when you pour the concrete, it can grip on the bar, right? Well, if you took that concrete element that's reinforced and you really heated it up or really cooled it down, you wouldn't want the concrete and the rebar to be expanding at different rates because then it would debond and it would want to crack. So it's sort of a nifty little thing about concrete and steel is that their alpha values are very, very similar. So they're not the same, but they're pretty close. So that really doesn't happen very much. So just a little factoid about civil engineering. Now, likewise, so there's a couple things about thermal strains and stresses that you need to be aware of. So first off, the fundamental definition for how we handle thermal loading on structures is related to strain. So we take a change in temperature and we multiply it by an alpha value, and that gives us a strain. So a couple things. If we want to determine a deflection, we would say, okay, I have strain, which is the change in length over the original length. So if I know what the original length is, I can tell you how much it elongates or how much it shortens, okay? So that'll tell you, so we can use this definition to determine a thermal deflection. And we can also use this definition to determine a thermal stress. So if we do the strain multiplied by E to get a thermal stress. Although this bullet right here, honestly, I probably this bullet right here, I should probably have it like red and bolded because it's really, really important. It says here that note that thermal stress only occurs if there is some degree of restraint, okay? And that's really, really important, okay? Let me go back to this image up here on the top right. So I have here just a box, okay? And let's say I've got this box and I heat it up, okay? If I heat it up, it's going to expand. And of course, it's going to make it larger. So I propose that that box is going to undergo some degree of thermal strain, okay? But the question is it going to undergo stress? Is it going to be a force per unit area? Well, I propose that for that box there on the top right, the answer is no. It's not going to undergo any thermal stress at all. It's going to undergo strain, but no stress. And that's sort of where thermal loading, it's one of the big differences with thermal loading. I mean, the only way that you get mechanical deformation is if you take something and you put force on it. You yank it, or you compress it, or you bend it, or what have you. How you get mechanical deformation is by applying stress. But you can get thermal deformation by not applying any stress at all. You can heat it up, and that'll cause it to expand, but it won't stress it. The only time that you ever get thermal stress is if there's some degree of restraint. And here's what I mean by that, okay? So let's say that I have a bar, right? Oh, my pen's getting all tangled. Let's say that you have a bar that's attached to the wall. So here's the wall, and you have some bar like this, okay? And let's say I take that bar and I heat it up, okay? Now, I propose that if you take that bar and you heat it up, what's it going to do? It's going to get longer, right? So it's gonna freely, you know, get longer like this, okay? Now, let's say for the sake of discussion that's all I have. I propose the bar is going to freely deform and it's going to experience thermal strain but no thermal stress. Now, let's add another wrinkle into the mix. Let's say that right over here, now I propose for a little bit that bar is just going to get longer and longer and longer, and then it's going to hit the wall, right? What happens if I keep heating the bar up? Well, it's not going to get any longer, but that wall is going to start to push back. The wall is going to offer some restraint. So because the wall is offering some restraint, now we're going to start to see some stress inside the member. So the only time you ever get thermal stresses is if there is some degree of restraint. Does that make sense? Is everybody okay with that? I really want that. That's a really important principle to understand with this class. And as a designer, whether you're designing in civil engineering or mechanical engineering, if you're worried about thermal stresses, one of the best ways to alleviate thermal stresses is to allow your member to move, okay? So like in bridge engineering, here's another bridge engineering example for you. One of the things that we use in bridges is we use fixed bearings on one end and we use an expansion bearing on the other end. So if I've got a bridge beam and I've got the two supports anchoring it to the ground, a fixed bearing is basically where you're taking the girder and you're attaching it to the ground. And we have a, like a plate. There's some holes drilled in that plate. Well, for an expansion bearing, the holes aren't just circular holes. They're slotted holes. They look sort of like this, like there's a little oval shape to them. And the idea is that from summer to winter, as that girder tends to want to get longer and shorter, that expansion bearing allows the girder to move a little bit. So by allowing the girder to move, you're reducing that thermal stress. Is it going to get longer and shorter? Yeah, it's going to get longer and shorter. There's nothing, you can't fix that. You can't change that. That's just physics. It gets hot, it's going to expand. It gets cold, it's going to contract. But you can reduce the stresses. And in terms of those stresses, you'll be surprised as to the numbers you can get. I've got a pretty realistic example coming up, and you're going to see some crazy numbers in terms of stresses. It's really, really shocking. Another thing, if you have your temperature varying as a function of X, in other words, like one side of the bar is getting hotter than the other side, which is possible as well, then in other words, if your temperature varies, you have to integrate. More often than not, this is pretty simple. I just wanted you to be aware of that. So if you wanted to define the total sort of closed form formula for deflection for axially loaded members, this would be it. This would be like the one formula that you would need to remember for axial members, period. Okay? So first off, if everything's constant, then this one just turns to PL over EA, and this just turns to alpha delta T. If you don't have any temperature load at all, this one goes to 0, and so on and so forth. So you can pretty much, it's one of those, that one formula will tell you just about everything that you need to know for temperature. Everybody okay with this? All right. So, bless you. So what I want to do is I want to talk about this example 9, okay? So let's take a look at some of these values, okay? Now I want to, illustrate this a little bit. So first off, I have a bar that's 100 inches long. So I'm talking about a bar that's, how many feet is that? Somebody tell me. We're looking at like 8 foot something, like 8 foot 4 inches. So we're not talking about something that's like unheard of. I mean, heck, the beam that's supporting the floor above this room is longer than that. So, pretty normal bar. The cross-sectional area, again, look, samurai sword and or a lightsaber right through the section has a cross-sectional area of 2 square inches. That's only about that big. So it's not that big. You're not talking about a bar that's really that big. The modulus of elasticity, that is a reasonable value for a modulus of elasticity of steel. Structural steel in buildings, we use 29 million PSI, so we got 30 here, so pretty reasonable. We have a coefficient of thermal expansion of 6.5 times 10 to the minus 6, and that's also a very reasonable value for a coefficient of thermal expansion. So what I have here is a question. If the load on the rod is 0 at 70 degrees Fahrenheit, compute the stress when the temperature drops to 0. So in other words, there's nothing going on the bar at all, and we installed this bar between these two walls at room temperature. So between these two walls at room temperature, okay? What happens when the temperature drops to 0, okay? What's the stress in the bar? So first off, probably one of the most important points is that the bar is rigid, okay? So let's have a little bit of a physics discussion about this. I'm holding this bar like this, okay? And then you know, Mr. Freeze comes in and tries to cool down the bar. What's the bar going to want to do? It's going to want to get shorter, right? But the walls are right there, and they're not letting it get shorter. So what type of force is the bar experiencing? Say it again. It's experiencing tension. The bar wants to get shorter, but the wall is having to pull it back, okay? So imagine what would happen if I took a flamethrower to it and tried to, heat it up. The bar is wanting to expand, and the wall isn't letting it, so that's putting it in compression. Does that make sense? Everybody okay with that? Okay. So if you understand that, I think the way that we perform this analysis is going to be pretty straightforward, okay? So let me go back to here. And let's write down some values. This is example 9. Okay. Excuse me. So we know that the length is 100 inches. We know that the area is 2 square inches. We know that E is, let's see, 30 times 10 to the 6 psi. We know that delta T, let's talk about delta T. All right, it is 70 degrees, and then we come in like Mr. Freeze and we cool the beam down, or we cool the bar down. So I propose that the change in temperature is minus 70 degrees. Now, I'll go ahead and say the sign doesn't really matter as long as you know what the bar is going to do. You know that the bar is going to get shorter. That's really what's most important. And we also have alpha, which is 6.5 times 10 to the minus 6. And then the units for alpha are always like 1 per degree Fahrenheit, something like that. Because the idea is alpha will tell you how much strain you have per degree Fahrenheit. So if I multiply it by a change in temperature in 70 degrees, that'll tell me how much strain I have. And what are the units for strain? There are no units for strain. It's unitless. So just something to keep in mind. Okay. Now, what I'm going to do for this problem is this. I'm going to assume that one of the walls is missing, okay? So what I'm going to do here, I'm going to say assume one wall is free, okay? And I'm going to write down here a little note because I'm going to come back to this here in a second. I'm going to say i.e. one wall is redundant. Okay, and I'm going to come back to that word redundant because I want to say something about that and how it can relate not only to indeterminacy but to a problem on your homework assignment. All right, so I'm going to draw that bar like this. Okay, so here's the bar, and it's like this. Okay, now this dimension is L. Okay. All right, so here's the bar, and now let's take that negative 70 degrees Fahrenheit. Let's take Mr. Freeze's gun and let's shoot the bar. What happens to it? It's going to get shorter, right? Make sense? So that's the bar before the thermal load. After the thermal load, that bar is going to be to about right here. And I propose that that length is L minus whatever that thermal deformation is. Is everybody okay with that? So that little bit that it gets shorter, that's delta T. We're with me on that? Now, help me out. How do I determine delta T? How do I determine that? How do we do that? I gave you the formula. Somebody's looking at their notes. We take the strain and we multiply it by the original length, right? So in this instance, we do have, you know, strain times the original length, because strain is change in length over the original length. And then to compute that strain, I'm going to say alpha delta T L. Okay? So to plug and chug, I'm going to get 6.5 times 10 to the minus 6, 1 over degree Fahrenheit, times, and then we'll, bless you, we'll go ahead and say this is minus 70 degrees Fahrenheit again, although the minus doesn't really matter. And then length is 100 inches. So what's that deformation come out to be? It'll be small, it's okay. Something like that? All right, I got a second on that? Okay, all right. So what we're saying is this. If that wall was gone, so remember, here's the bar. I got the bar here and here. Let's let go of the bar right here. If I apply that thermal load, that negative 70 degrees, you're telling me the bar is getting shorter, right? I propose that that's not what's really happening. What's really happening is that wall is there, okay? And so what is that wall doing? It's taking that bar and it's yanking it back, right? So what we need to do is this. This is what we need to do. Therefore, and I'm going to write this out so that it makes sense. We need, oh goodness, that's an N, not an M. Need to determine what wall reaction would cause a deflection of plus 0.0455 inches. Does that make sense? So in other words, what is this? So here's the bar. It's going to get a little longer, and it's going to get longer because the wall is having to yank it back. So what is that force required to generate a delta of 0.0455 inches? Because the idea is this: what happens if I superimpose those together? What happens if I take a bar and I cool it to where it gets shorter by this amount, and then I take that cooled bar and I yank it that amount? It goes back to 0, right? So whatever that force is, that's how much the wall is yanking on it. Sound good? So how do we determine that? Well, how do you determine deflection at all when you have a bar and you're yanking on it? Well, PL over EA. So delta equals PL over EA. And the one value that we do not know in this expression is P, because we know L, we know the A, and we know the E value. So therefore, P is EA over L times delta. So that is, E is 30 times 10 to the 6 PSI. We have A is 2 square inches. We have delta, which in this case is 0.0, bless you, 455 inches. And then over an L of 100 inches, not L, right? 100 inches. Everybody got a number? 27,300 pounds. Remember, it's a P, it's a force. Do I have a second on that? So that's how much the wall is having to hold that bar back to keep it at a constant length. Now, was the problem asking for the force, or was it asking for the stress? I think it was asking for the stress, right? And how do we compute the stress from that? Divide by the area. So therefore, stress is force over area, which is 27,300 pounds divided by 2 square inches. And so that comes out to be 13,650, you said? I want you to think about that number. I mean, really think about that number. I'll admit that I remember that one. It was like, I think it was example 5, where I had the bar that was like 5,000 feet long. That value was a little out there, and I was using an out there value because I wanted to make a point about that problem. This problem's a little different. Every value that's in this problem is easily conceivable. Okay, we're talking about a bar that's just over 8 foot long. That's about that big around. Okay, and a temperature change of something like 70 degrees. Okay, look at this stress. Right? Think, how much stress does your car put on the ground? 32 psi, whatever's in your tires, right? That's 13,000 psi just to hold the bar straight. That's a lot. Okay, so I'm telling you, what temperature can do is a little crazy sometimes, like what it's able to achieve. So it's just it's fascinating. So any questions about this? This is good stuff. Any questions? All right. Okay. Now this one, I about moved on. Okay, I do want to make a point. Okay, I did mention a term here, and this term here is this word redundant. I want to make an observation about this term redundant, and this is going to kind of relate to axial loads and to your homework assignment. Okay, what we did for this problem is we treated the wall on the right as the redundant. In other words, I removed the wall from the right and I just picked one. Let me ask you a question. Do you think it would have mattered if I removed the wall on the left? It had been the same thing, right? What we're using here, and we'll actually mention this for those of you in structural analysis near the end, but we're using a method in analysis called a method of consistent deformations. What that means is you pick a force that is a redundant. In this case, for this problem, we picked the wall on the right as the redundant. Okay, and what we did is we did 2 analyses really. One with the redundant removed, and one with the redundant applied. And we added the 2 up. And the way that we were able to solve it is we kind of used a compatibility relationship. I know it didn't seem like what we did. Our compatibility relationship is that this thermal deformation has to equal that mechanical deformation. And so that was a redundant analysis, or an analysis using compatibility. And that's what the method of consistent deformations is all about. So I want to make a note about that here on this next slide, because I think this is worth mentioning. So I'm going to call this a homework hint, and it's on external indeterminacy. Okay. On external indeterminacy. Okay. So I want to draw a generalized figure. Okay, so here's a bar. Okay, and it's got all sorts of different loads on it. It's got, a load right here, a load right here, maybe distributed load. all sorts of different loads on it, okay? Now, I propose from a statics perspective, if I've got all these different loads on it, I could take the bar and I could heat it up, I could cool it down, what have you. I propose that there are two reactions, right? There's a reaction this way and a reaction this way, right? And so let's just make up some names. Let's call this support A. Let's call this support B. And so maybe our reaction names are AX and BX. Is everybody okay with this? And don't apply any magic to the loads. I'm just making some values up. It could be anything. I could have loads going any which way. Okay? Now, if I sum forces, let's say in the x direction, what I'm going to get is I'm going to get a to the x going to the left, or ax going to the left, bx going to the left, and I'm going to have all this other stuff going to the right. And all it's going to tell me is that ax and bx have to add up to give me all of this. But it's not going to tell me what AX and BX are. It's just going to tell me that they have to sum up to add those loads. So this is indeterminate, okay? So here is what's going to happen for an externally indeterminate problem. What we're going to do is we're going to split it up into two analyses, okay? Now, for this analysis, what I'm doing is I'm going to choose BX as the redundant. And you'll see what I mean. Okay? So I'm choosing BX as a redundant. I don't have to choose BX. I could choose AX. I could choose any one of my unknowns as a redundant, but I'm going to choose one of them. And I'm going to split this into two separate problems. I'm going to say that this equals this problem plus this problem. Okay. All right. What I did is I chose BX as the redundant, but I could have been anything. Okay. So what I've done is I've split it up into this problem, which if you want some names for it, we'll call this the primary structure. That's a good question. I'm gonna mention that here in a second. And then BX, we'll call this the redundant structure. Now his question was, does AX go in the primary? I'm going to say no, and here's why. I'm going to say that on this structure, I'll get maybe like an AX1, and this structure, I'm going to get like, we'll call this, I don't know, like AX2. And I'm saying that when you add those two up, you'll get this. But AX actually really isn't going to matter for the analysis. And just bear with me. I think you'll see what I mean. All right. Let's take a look at the primary structure. I want to pay attention to point B. So this right here, this is point B. This is point B. On the primary structure, do you think point B is going to move to the right or to the left after you apply those loads? Like if I take these loads and I apply it, what's going to happen to point B over here? It's going to go to the right, right? This is going to get longer, right? So the bar from beginning to end is going to stretch out a little bit. Some degree delta, all right? So if you want to name it, we'll call it delta primary. Okay? Now, what do you think is going to happen for the redundant structure? What's going to happen to point B? Is it going to move to the right or is it going to move to the left? It's going to move to the left, right? So that's going to do this, and we're going to call this delta redundant. What can you tell me when it's all said and done about delta primary and delta redundant to deal with? They're equal, all right? And so what you can do is you can set delta primary equal to delta redundant, and you can use that to solve for Bx. Then you go back to the original structure, some horizontals in the x direction to get Ax. So that's going back to your question about is Ax on the primary or the redundant, and I'm going to say it doesn't really matter because once you've got Bx, you're going to go back to the original structure to get Ax. Does that answer your question? Is everybody else okay with that? What I am saying is you're going to have to do that on the homework assignment. So that's sort of where the homework hint is. Any questions? It's not too bad, right? Okay. All right. If you're okay with that, now I want to move on to our last example for thermal. This one's a little more involved, but it's not that bad. Okay. Here I have a bar. This bar is out of brass, so the material properties are a little bit different. So we have a different Young's modulus and a different coefficient of thermal expansion. Now, what I have here is a bar length, and see where it says undeformed at 50 degrees Fahrenheit? At 50 degrees Fahrenheit is the initial temperature. That's like the temperature before we're applying any load. So the initial bar length at 50 degrees Fahrenheit is 60 inches. This is a 5-foot long piece of brass. The yield stress for brass is 15,000 psi. Remember, anytime that you ever see a yield stress in a problem, you're usually going to be asked, is the structure performing adequately? What's the factor of safety? Or is it behaving elastically? And we'll look at that here in the end. We have a bar, it's a circular bar, it's a round bar of brass, and the bar diameter is 1/2 inch, okay? Now we have a load applied at the tip of the bar, some load P, we don't know what P is, we'll figure that out, but we do have a thermal load. Now the thermal load is not constant for this one's varying, so imagine that this piece of bar is, I don't know, in some engine or some mechanical gizmo where it's getting hotter on one end than it is on the other. So in addition to P, the bar is heated along its length. So it's 50 degrees at the beginning, and it's 150 degrees at the loaded end. So it's getting hotter for that load P, okay? So we're going to have to handle that appropriately. So what we need to do is determine what is P such that the allowable, or such that the rod doesn't deform more than 0.08 inches. In other words, this brass bar has a limit as to how much it can stretch. So what we're going to figure out is what is P so that we don't exceed that load. And this is a very common type of analysis for a civil or mechanical engineer trying to assess a given structure and figure out what's its maximum capacity under a given limit. In this case, the limit is that the deflection is 0.08 inches. And then we're also going to ask, at that load, is the rod behaving elastically? And we'll look at that here at the end. But let's write down some values, and let's see if we can do some analysis. So, all right. So let's write down some values. So first off, we have an E value of 15 times 10 to the 6 psi. Remember, E values are going to be big. They're like 15 million, 10 million, what have you, psi. We have an alpha value of 10.6 times 10 to the minus 6. And remember, alpha is 1 per degree Fahrenheit. Okay. We have a bar length of 60 inches. Now, I'll go ahead and put that is at 50 degrees Fahrenheit. Okay, and that's going to become important here in a second. All right. We have a yield stress of 15,000 psi. And then we were given the bar diameter. So the bar diameter is 1/2 inch. So what can we do with that bar diameter right off the bat? Find the area. So pi over 4d squared. So area is pi over 4d squared. So pi over 4, 0.5. Oh, what happened there? Squared, and that comes out to be what? There we go. 0.196 square inches. All right? And we know that our delta allowable is 0.08 inches. So what we're trying to figure out is what is P. That's sort of what we're trying to figure out. Okay? Everybody okay with that? Now, that temperature is a little unique. So let's see if we can figure some stuff out about that. Okay? Now, so let's look at temperature effects. All right. Okay. So what the problem is stating is that, let's go back to that, because I want to read it verbatim and make sure that we're understanding what it says. Okay. Right here. In addition to P, the bar is heated along its length, and the temperature is found to vary linearly from 50 degrees at the fixed end to 150 degrees at the loaded end. Okay? So one of the things I'm going to go ahead and right off the bat and do, because I've got linear variation, so I've got a function. I'm going to start to define some coordinate systems and some values, something to go off of. So here's my bar. And I have a load here. What I'm going to do is I'm going to start to define some coordinate systems. It's almost like, I got a coordinate system right there. So what would the x value be, like right here, and what would the x value be right, oops, sorry, wrong one. What would the x value be here and here? Now, remember, this bar is 100 inches long, so that L equals 100 inches. Or 60, I'm sorry, 60. Would it be a fair way of stating this that at the beginning x equals 0 and at the end x equals L? Is that a fair way of looking at it? It's not bad, right? To help me out, at x equals 0, what's the temperature? What is the problem state? The temperature is what? 50 degrees. And at x equals L, what's the temperature? Okay. Now, when we look at thermal loading and thermal effects, do we really care about what the temperature is, or do we care about what the change in temperature is? The change in temperature. So let's look at the free end, because I think it's a little easier. At the undeformed length at the very beginning, what's the temperature of this bar? 50 degrees, right? So what's the change in temperature at the end? 100. What's the change in temperature here? 0. Okay, there we go. That's something I want to make sure that everybody's clear on. So over here, the change in temperature is 100 degrees Fahrenheit, and the change in temperature is 0 degrees Fahrenheit. Sound good? How about this? They said it varies by the linearly, right? So maybe what we need is the equation of a line. At x equals 0, here's a value, and at x equals L, here's a value. So how do I determine the equation of a line? I need a slope and a y-intercept, right? So how about this? The slope is is that. So, well, here, let's leave it symbolically. So this is delta t2 minus delta t1 over L minus 0, right? And remember, this delta t1, so that's 100 minus 0, 0, right? So I'm going to say delta t2 over L. So if you want up here, we'll call this delta t1. We'll call that delta t2. Right? So that's the slope, and the intercept is the value of delta t at x equals 0. And what is that? 0, right? Because it's delta t1. So therefore, I have that. What do you think? Is everybody okay with that? That's not bad, is it? Okay. If you understand that, then I want you to look at this. We'll look at this real quick. This is my expression for deflection. Okay? Now, you agree I can split this up into two integrals, right? The integral of the first fraction plus the integral of this, right? Let's look at that. Does our bar in this problem have a constant area? Does it have a constant load, a constant mechanical load? Yeah, it's just P, right? So I propose that for our problem, what we're going to have is delta equals PL over EA plus the integral from x equals 0 to x equals L of alpha delta T dx. Everybody okay with that? So if you want, we can call this delta mechanical. We can call this delta thermal. Did I blow your mind with the calculus, or is that fine? It's not so bad, is it? All right. Let's look at this delta thermal. Let's see what we can figure out here. Come on. All right. So let's look at this delta thermal. So that's the integral from x equals 0 to x equals L of alpha delta T of x dx. And if you want to put that like in brackets or something, you can. So plug and chug, I've got the integral x equals 0, x equals L of alpha, and then I have that. Everybody okay with that? Let me ask this. Is this alpha, is that a constant? It's a number, 10. Is delta T2, is that a constant? Yeah, because that's just 100, right? Is L a constant? Yeah, that's 60, right? The only thing that's not a constant is X. So I propose, let's factor all that out. So I have alpha delta T2 over L, then the integral from x equals 0 to L of x dx. And if you're wondering, like one of the things I like to do when I write integrals, especially with a class like this, is I always like to do like x equals 0 and x equals L. I don't put just the 0 and the L, because when I do that, I know that x is the variable, so it helps me determine what's a variable and what's not. I know sometimes in here it can feel like alphabet soup, so I try and do that. So now that we've got this, this goes back to Calc 1. What is the integral of x? Anybody remember? 1/2 x squared, or x squared over 2. So this is, so I told you the calculus isn't that hard in here. So it's alpha delta t2 over L times the quantity x squared over 2. And that's evaluated from x equals 0 to x equals L. Now what happens here? I plug in the top value minus plug in the bottom value. When I plug in the bottom value, I'm just going to get 0, right? For the top value, I get L squared over 2. So bring the 2 out, and then the L's cancel, right? So I'm going to get, here, I'll write that out. So I have alpha delta t 2 over L times L squared over 2 minus 0 squared over 2. So I'm getting delta thermal is alpha delta t2 L over 2. Is that okay? Let's plug and chug, because we can calculate that now, right? Like, we got everything we need. We got the alpha, the delta t2. Let's just go ahead and do that now. Let's see what we get. So we get 1/2 of alpha. Alpha is 10.6 times 10 to the minus 6, 1 per degree Fahrenheit. Here, let me move this down a bit so it's a little easier to see what's going on. Then we have 100 degrees Fahrenheit, and we have a length of 60 inches. So what are we getting here? Zero 318. Is that what you said? Do I got a second on that? Anybody else get that? Okay. All right. Good. Okay. Let's think about what we ought to do with that value. Let's think about that. Let's go back to the problem. Here's the problem. Okay, I got a bar that's seeing 2 types of load, right? It's yanking on the end, and it's getting heated up. Now, what we just found is that temperature causes a deflection of what? What was it? Would you say 0.0318? Okay. Well, what's this say here? Determine the magnitude of P if the allowable elongation of the bar, of the rod, including the temperature effect, is 0.08 inches. So tell me, what do you think we need to do? If we know the temperature causes a deformation of 0.0318, what do we do? Subtract it from that, so we get like 0.48 or 0.048 something, and then what? Exactly. We figure out what load P causes that difference. That's what we're doing. Okay, so let's do that. Let's see what happens. All right, so does everybody have this? Do I need to leave this up here for a second? It's okay if I do. All right, okay. Wait, I have example 8, but we're on example 10, aren't we? That's 10. Get that mouse pointer out of the way. So we found that delta thermal is 0.0318. So therefore, delta mechanical has got to be 0.08 minus 0.0318, which is, what'd you say? Or what, I didn't ask. 0.0482. Okay? And then for this structure, remember, over here, we know that L is 60 inches. We know that E is 15 times 10 to the 6 psi. And we computed A, right? And what was that? I don't remember. There we go. There we go. So how do we compute delta mechanical? We take, like, what's the formula? Delta equals what? PL over EA, and the only thing we don't know is P. So if delta mechanical is PL over EA, P is EA delta mechanical over L. That's similar formula to what we just used, just flip and multiply. So we got 15 times 10 to the 6 psi. We've got 0.196 square inches. We got 0.0482 inches, and we got 60 inches. All right, so what do we got here? What, if we plug and chug, what do we get?
2,362.
2362. Do I got a second on that? It's what are the units? Pounds. Yeah, remember, this is a load, and everything's in pounds, inches squared. So I'll put over here. P, there we go. So pretty simple, right? Now we're not done, because there's something else that the problem asked. The problem has another thing to throw at us. At this load, is the rod behaving elastically? Let's talk about that. Now, I propose, so we'll look down here, let's say check elastic behavior. I propose that whenever we have to check whether or not something is behaving elastically, what we're doing is we're looking at its stress. And we're seeing if that stress, how does it compare with what? The yield stress, okay? Now, I also propose that in general, to compute the stress for an axially loaded member, we would take the mechanical stress and add it to the thermal stress. Now, right off the bat, is there something you can tell me about one of these values? The thermal stress is 0. Why is the thermal stress 0? Because it's unrestrained. For this problem, remember, the only time that we ever get thermal stress is when there's some degree of restraint. Like with this previous problem, we got thermal stress because the bar was being held in place. If I take this bar and I heat it up, cool it down, do whatever, it's just going to get longer or get shorter. It'll strain all day long, but it will not undergo stress. I propose its thermal stress is 0. The only stress that you get from this problem is from mechanical loading. So I propose the only thing we need to do is P over A. So what is 2362 pounds over 0.196 square inches? What is that? Say it again. 12,000 point, or 29? 29. Do I have a second on that? Very good that? All right. Is it behaving elastically? Yes. Why do you say that? And remind me, what was the yield stress? 15,000. All right. So now this is factor of safety. Anybody remember how to do that? The factor of safety against yielding. I'm just quizzing you on that one. There you go. What'd you get? 1.25. I got a second on that? So it hasn't yielded, and it's got a factor of safety of just over 1. Now, we're close, I mean, but we're still in elastic range, okay? And so you can use that factor of safety always to sort of judge whether or not you're good or not. And some cases you might be, some cases you might not. So yeah. Any other questions? This is good stuff. Not too bad, right? All right. Before we call it today, because we do have a little bit of time, I want to introduce our next topic, okay? So I sort of like to think of this class in like modules, if you will, like big chunks of material. And I would say that right now we just finished our second big chunk of the course. The first chunk being just the fundamentals, like what is stress, what is strain, what is, their relationship, like Young's modulus and all that stuff. And then our second big chunk is on axial loads, taking something and yanking on it, taking something and pushing on it. How much does it deform? What are the stresses? What happens when you heat it up? That's our second chunk. Now we're going to switch gears a little bit, and we're going to talk about torsion, okay? Now, when I'm talking about torsion, I'm talking about this, okay? I'm talking about taking something and twisting it, okay? Now, that might seem like a big jump, like you were talking about this, now you're talking about this. It seems different. Well, it is different, all right? The mechanics are different, the parameters that we use are different, but what you are going to find when we get into this is that the equations are very, very similar. For instance, with deflection, we would take PL over EA, okay? That delta would be the amount of deformation, how much it gets longer or shorter. With torsion, what we're going to be looking at is the angle of twist, how much it changes, how much the angle changes. And the formula is going to be this. And I don't want to get too heavy into it, but you're going to find that there's some very striking similarities. Like, for instance, E is a material parameter, right? That's Young's modulus. That's different from material to material. G is a material parameter. It changes from material to material. A is what we call a section property. You take a samurai sword or lightsaber through a cross section and you look at the section. A is a property of that section. In other words, it's the area of that section. J is a property as well of a section. It is a different property. It is not the area. It is what we call the polar moment of inertia, and I'll explain that in a little bit. But it is, again, a property of that section. P is your applied load. T is your applied torque. And then you have the member length showing up in both of them. So the formulas are very, very similar. So it's a very natural step, to go from axial load to torsion. Now, I'm going to tell you something right now, and this is something that you can set your watch by, something I will not do to you, and something also that you should try and avoid in practice, okay? When we looked at axial loads, we honestly really didn't care what the section looked like. We were samurai sorting or lightsabering through the cross-section, and it didn't matter whether or not it was a square bar, a round bar, a pipe. It really didn't matter. All we needed was the area, okay? Well, for torsion, it matters, okay? You can set your watch by what I'm about to tell you. I will never, never in this course give you a torsion problem of something that is non-circular, okay? In other words, you are either going to be dealing with solid circular shafts or you are going to be dealing with pipes, okay? Period, okay? There is a very specific reason for that. And I didn't bring my little deformable beam. I'll try and bring that on Tuesday because you can actually kind of see it. When you have a circular cross-section, a circular section like this, and you twist it, just the physics of the situation will tell you that what happens is you have to twist it and it rotates. And that's it. Circular cross-sections do nothing more than twist. Whereas if you have something that's non-circular, it does something a little bit more. not only does a non-circular cross-section twist, but it also does something called warping. Non-circular cross-sections, not only do they twist, but they deform in and out of the plane. Okay, and that's just something related to sections that are non-circular. So from a design standpoint, it's usually advantageous to avoid torsion whenever you have something that's non-circular. If you ever look at a lot of mechanical design, anytime that you have something that's going to be twisted, more often than not, it's going to be circular. It's either going to be a shaft or a pipe, and that's why. Because if you're connecting that, that circular shaft, or if you're connecting that shaft to an adjacent component and it's non-circular, it'll warp and it'll butt into that adjacent component. So we try to avoid torsion in non-circular sections. There are some cases where it's unavoidable and you have to deal with it. And if you have to deal with it, I'll say two things. A, the math and the mechanics get a lot more challenging. And B, we usually only have to deal with it in very specific situations, and a lot of times the math is already solved for us. For you civil engineers, one of the times that we have to deal with torsion is when we look at beams. If you have a steel beam and it's being bent, the top of the beam is experiencing compression, let's say, and the bottom is experiencing tension. Anything that's in compression likes to buckle, but with beams and like I-beams that are being bent, when they're experiencing compression and part of the beam is experiencing tension, there's a stability issue with the beam. It doesn't really know how to handle it because it wants to buckle. Like part of it wants to buckle and part of it doesn't. And the only way that it can handle that failure is by kicking out and twisting a bit. And it undergoes a particular failure called lateral torsional buckling. And so you have to understand a little bit of the mechanics of torsion in order to understand that math. But fortunately, a lot of that stuff's already solved for us, and it ends up being a pretty plug-and-chug expression. But just in general, as civil or mechanical engineers, if you're going to have something that's going to be twisted, make sure it's circular, that either a shaft or a pipe. It's very, very, very important. Let's see, what time is it? It's 9:07. I'm not going to get into a heavy amount of this derivation today, but I do want to mention a couple of points. What we're going to be doing to derive this torsional expression is we're going to look at a torsional shaft sort of before and after deformation. And what you'll see is if you look at just a small little piece of it before and after it deforms, it looks a lot like this. And I'm going to time warp us a little bit. Come on. Actually, let me just do this. Yeah, I know, time warp. It's just a jump to the left. All right. What we're doing is we're ultimately seeing when we look at a small little element before and after torsion, it ends up looking like this. So what we're going to be defining is a relationship related to the shear strain, okay? And so we're going to be taking that and doing some calculus to sort of define that over the cross-section. And ultimately what will happen is this, and I don't want to get crazy into the math today, but I want to show you a couple of things. Goodness gracious. We've gone through a lot of slides in here. I talk a lot, I must. Okay, I don't want to get too heavy into the math, but what I'll say is that we're going to do a little bit of derivation to try and define angle changes and what have you. And I'm going to skip a lot of this to sort of indicate once we define a lot of our expressions and start integrating it out for your purposes and for your purposes in doing problems, what ends up happening is a lot of this ends up getting factored out into one big integral. And this one big integral is a function only of what the cross-section looks like the shaft or the pipe or what have you. And so because it relates only to the cross-section, we define a new cross-sectional property, and that cross-sectional property is called J. Now, I want you to relax. You aren't going to have to do much integration for that because a lot of it's already solved. If you have a solid shaft or a pipe, you can calculate J pretty easily. It's really plug and chug. But I do want to walk you through that derivation next time so that you understand a little bit of where it's coming from. And then again, like I said, when it's all said and done, you're going to have formulas that are very, very similar to what we had for axial loads. So it's a very natural next step, is axial loads and torsion. It's also the reason why on our first exam, you're going to have fundamentals of stress and strain, and then you're going to have axial and torsion, because they go very well together. So it's not like you're having to remember all this different crap for the exam, whatnot. But remember, we don't have exams in college. We have celebrations of learning. So that was, yeah. I saw you're like, yeah, real funny, real funny. All right, any questions? All right, that's all I got, guys. You all have a wonderful weekend. I will see you on Tuesday. One more thing, don't forget, next Thursday, your homework is due. So come prepared to ask some questions on your homework on Tuesday if you have any. That's all I got. We'll see you.